The difference between particle energy and wave energy. There's a big difference. So if you have, let's say, a ball and you throw a ball, that ball has kinetic energy, and the person throwing the ball gives that ball some energy when he tosses it, and then a person catching it has to absorb that energy, right? Change that kinetic energy, and it either it turns into friction and all kinds of interesting things. But it's a lot different when you have, let's say, a rope. Well, with the ball, there was a physical transference as well as the energy being transferred. All right, an object was moving. But when you shake a rope, like if you have a rope or a hose or something, or a slinky, and you put a little bend in it, I'm going to get some slinkies from school this week, and you knock it, a wave will pass through it, and the energy will move through the rope, and the person on the other end can feel that energy, but the rope didn't move. So the rope, you didn't throw the whole rope at someone or the whole hose at someone to be able to transmit energy. And so what's interesting is a wave can transmit energy through matter or space. So you don't have to have matter to do it. And again, there isn't any real particles being transferred when you have a wave go by. The first thing we're going to talk about are mechanical waves. Actually, that's all we're going to talk about. I think this chapter is pretty much, well, I can't remember, but part of it at least. Mechanical waves. These are all waves that we're going to talk about, except electromagnetic waves. And when I say electromagnetic, we're basically talking about light, anything that travels at the speed of light. And mechanical waves require a medium. You need to, for that wave to go through, you need some kind of a medium or material for it to go through. Here we start off really easy. A water wave, right? You need, so like a tsunami, or just a regular wave at the beach. Obviously, the medium, so a water wave needs the medium of water. In air, what kind of wave can go through air? We can have sound, a sound wave travel through air, for instance. Or actually also like a shock wave can do that too. And rock, what can we have travel through rock? You could have, if you had earth science, an earthquake wave go through, or as well sound, because sound definitely can travel through rock, and in fact we'll find out later it travels faster through rock than it does through air. All right, so those are just examples. Then again, at one point in time, you may have learned about different kinds of waves in how they travel. The first kind are called transverse waves, and hopefully we'll do a lab this week. Well, I'll do a lab and you get to watch and collect some data on a slinky lab where we can do show a transverse as well as when we get to a longitudinal wave. So transverse waves vibrate perpendicular to the direction of a wave's motion. Here's a little picture here. If you send out a wave, like go like this, then the wave motion, the velocity of the wave is in this direction. You'll see that little bump travel like this. But to make that wave, you had to make your hand go up and down. So that's where it's perpendicular. So you move your hand up and down while the wave travels this way. So obviously an example is a wave in a shaken rope. Another one though are earthquake S waves. Again, if you ever did any seismology stuff with earth science, S waves or secondary waves are one type of earthquake waves that are studied by a seismograph. Okay. A second way we can have waves travel are longitudinal waves. The wave pulse or movement is in the same direction as the wave motion. So we can do that, set that up in a slinky as well. Not so easy in a rope, but in a slinky, If you pull back or shove, imagine you did a forward shove, you would get a compression here, and you get a compression wave traveling. Now you move your hand, side to side, and the wave also travels side to side. So longitudinal waves, it's parallel versus the perpendicular here. What kind of things do this? With a compression wave like this? Well, sound is a big one. With sound, which is a whole separate chapter, I think that's chapter 12, you have particles that are in air. Imagine a bunch of particles. And how you can do that is you have some kind of a diaphragm or something. Shove this, and they end up running into each other, and then they run into each other, etc. And you get these compressions that travel, but when your hand is moving the opposite direction, you might want to call it decompressions, but the fancy word for the stretched out areas of the slinky is called rarefaction. Really strange word there. Now, earthquake waves, P waves, or the primary waves, travel this way. What's impressive about this type, longitudinal waves can travel through liquids. So P waves can travel through liquids. What makes this interesting when you study seismology or in earth science is that here's a little picture of the earth, and imagine there's an epicenter, so an earthquake starts here. S waves, there's a little bending going on. We don't know about that yet, but so you get some refraction going here. And look what happens there. If you were standing on the other side of the earth with your seismograph, you would not be able to sense the S waves. Why? Because they can't go through that center part. And what is there? Well, we have a liquid core. And so S waves are stopped by the liquid core because you cannot, think about this action. You can't make this quite happen you can't move up and down here with an earthquake wave and expect other stuff to move. And so, yes, so S waves, this doesn't happen, but the P waves can travel through the Earth's core. And that is, in fact, how we know we have a liquid part in the center of the Earth. All right, another type of wave, they seem kind of close to transverse waves, but they are still different. Surface waves have characteristics of both transverse and longitudinal waves, and particles move both parallel and perpendicular to the wave motion. And surface water waves are an example of a surface wave. And earthquake waves, they're called a Rayleigh wave. And they happen to be the most damaging type of earthquake wave. Let's see if we can figure out why. If you see a little picture of what happens on a surface wave, you might have some misconceptions actually about this. If you are floating in a little inner tube on the ocean, and we wish we could be all doing that now, and if that was happening, watch the motion in this play-by-play here. In this motion, you do not, if a wave comes, you do not travel with the wave. The wave, you are part of the wave, and you go up, you go back, you go up, you go down, and you move back again, and you end up moving in a circular motion. Both transverse and longitudinal properties there. For an earthquake wave, this is the most damaging kind of wave. First of all, they travel on the surface. And what do they make a building want to do? Move up, down, left, and right. And so therefore that is damaging. All right. Let's talk about some measurements we can make with waves. One is the speed of a wave. And there are two ways we can do speed of wave. One is our old-fashioned way, basically distance over time. So change in distance over change in time or displacement. And another way is V equals F times lambda. I don't know if you know lambda yet. Lambda, that's a Greek symbol, lambda, and it represents wavelength. I'm saying this now because, again, depending on a story problem, sometimes you'll use this. You have this information. You can watch a wave. For instance, an earthquake, a water wave, and you would know the time it takes from a certain distance out, to travel, and you could find its velocity that way. But if you have its wavelength and also its frequency, then we can also find out that information. All right, which I think with our lab we need this later, our Slinky lab. All right, so what does the speed depend on? Depends on the medium through which a wave moves. It does not depend on how much energy you give a wave. For instance, if you go back up to the Slinky and you push and yank on it super hard, you cannot make that wave travel faster. All right? If you slap water and try to make a water wave, you can make the water wave bigger, but you cannot make it faster. It depends on the medium, so it depends on water. What about sound? If you yell louder and yell forcefully, can you make the sound travel faster? Nope, because it depends on the medium. It depends on the temperature of the air, humidity of the air, and all that kind of stuff. Okay? And something that's called elastic density of air. That's what it depends on in that case. All right. So water wave depends on depth of water. Sound wave depends partially on air temperature and other things. Spring waves depends on the tension and the mass of the spring. That'll be interesting and again can be discovered in a lab. All right. Next page. Other characteristics of waves, things that can be measured and we need to know, and that is amplitude. That is the maximum displacement from equilibrium. We saw that in the last set of notes what amplitude is. This depends on how much work is done. All right, so there's energy involved here. And it turns out the energy is proportional to the square of the amplitude. For instance, if you have a wave that is twice as tall or high, how much energy does it have now? It has 4 times the energy as compared to the other wave. Wavelength, I think again, did see that in the other notes, is the distance crest to crest. Its symbol, like I just mentioned, is lambda. And this is just the formula switched around from the last sheet, is lambda equals wave velocity divided by wave frequency. All right, what else can we do? We can have waves, if we have more than one wave, where we can make waves in phase. In phase is when points are pretty much in line, in step with each other. So I don't think you can see this unless you printed out the notes, that there is a blue line and a pinkish line on top of each other. These are 2 waves that are in phase. They are moving together. You might, if you are into music, you can have someone clapping and you can have someone else clapping at the same time. All right? Then that is an example of things being in phase. All right? And this is an example, this next picture, when things are out of phase. These 2 waves are not doing the same thing at the same time. Okay? This last picture is you can have 2 waves that are out of phase, actually. They're 180 degrees different from each other. And they are, in a sense, undoing each other. Okay? We're going to find out these waves actually can cancel each other out. All right? Another term we need to know is period. We already know that from circular motion. T, it's in seconds. Time it takes a point on a wave to return to its initial phase. Okay? And once again, this is different. This depends on the source. So the period and as well the frequency, these depend on source. What do I mean by source? Whatever's creating the wave. If it's you, if you are tapping on, if there was some water and you're in the bathtub and you tap your hand on water, every time you tap, you'll make a wave. If you tap faster, you're going to make a lot of waves. All right? When you have a lot of waves, isn't the period shorter then? And what about the frequency? These are inverse to each other. So if you tap really fast, you will have a high frequency. So whatever is generating the wave will determine the period and frequency. The speed of the wave is dependent on what that wave is traveling through. Okay, wave behavior. What can waves do? Well, waves at a boundary, that means when they run into something or run into a difference in medium, one option is they can reflect back, or in other words, bounce back. Another thing a wave can do is pass through into another material, if some waves can do that, some can't. And some can pass through and change direction. And that gets really interesting. It's especially with light that we like to study that. All right, more terms. Incident wave is the wave that strikes a boundary. For instance, if you had a light wave and a light wave hits a mirrored surface, this would be considered the incident ray, that's a wave, a light ray. And then you could have, let's say, a reflected ray. Okay? All right, that's the returning. And we'll find out later that this angle equals this angle, which is the simplest law ever in physics. Okay. So depending on what's happening, a returning wave could be inverted or upright. What do I mean by that? If I send a wave like this, let me do this right. Yes, okay. Then the reflected wave can do this. This is normally what we're going to see. So this is inverted compared to this one. And this is what happens. It's inverted when you hit a stiff or rigid. For instance, if I have a slinky or a rope and I tie one end off to, let's say, a wall, it will always be returned. I can flick this, it will be returned inverted. Always happens. So that's because this is a rigid medium. Okay. Last page here. All right. Other things that can happen. Superposition, kind of shown on that last page. Two waves can exist in the same place in a medium at the same time. And we can have a principle of superposition. These are some dorky pictures I stole, sorry, from the internet. Because they're not very wave looking. So someone just, drew pictures of this. Imagine we have this wave bump and this wave, and this one obviously is inverted compared to this one, and they head towards each other. There is a principle of superposition that says this: the displacement of a medium is the algebraic sum of the displacements caused by the waves. What does that mean? This plus this, okay, becomes this plus this, and notice when they form in this picture, actually one was right here and one was right here. And what do we mean by the algebraic sum? This one had a positive x displacement, this one had a negative x displacement, and when you add them up, what do you get? You get 0. Here it was a little bit, those cancel, these cancel, these cancel, these cancel, these canceled. So what do you get? Nothing. Now, the amazing thing is those waves didn't go away. They don't disappear. What happens is those waves are still traveling and they actually separate out and they reappear, which is pretty darn cool. All right, this is called destructive interference. Why? Because we see that they canceled out. We can have constructive interference. So here we have a hump wave, and this X wave and Y wave have both a positive amplitude. And guess what? When they run into each other, if this had an amplitude of 1 and this had an amplitude of 1, guess what this amplitude is going to be? 2. It is just the sum. And again, that doesn't stay. That wave Y is still traveling this way, and wave X is still traveling this way, and they will separate. And you can do this on a slinky, which is pretty darn cool. All right. A node is the point at which a wave doesn't move at all. And an antinode is the point of largest displacement, which are things that we see when we make a standing wave. We can have a standing wave, and when you perfectly align a wave, when you send a wave out and it reflects back and it is an opposite, it's inverted, it appears, and that's kind of like the picture oh Lord, let me see if I can do this right. I'm going to start from the wall. That's easiest. So imagine you sent a wave like this. Oh, it's not very even. It will reflect like this. And you have nodes. And we normally don't count. We count the middle ones. We normally don't count the ends, the place that you're holding and the place that's attached to the wall, but whatever. And then this would be an antinode right here. I'm going to put on a separate page all the cool YouTubes that you can watch of people making standing waves on ropes, and then also standing waves in a university large pool that is meant for generating waves, and it's pretty cool and kind of crazy to look at. All right. When do we do destructive interference? A good example of that is noise-canceling headphones. They work on this principle of destructive interference. You have an outside sound, and your headphone generates a sound that is an inverse wave to that to cancel that out, which is pretty darn cool. All right. Am I done? No, I forgot. There is another page. All right, some last things again that just have the coolest videos, and I will put these up if you didn't look these up already. I'll try to put them all on one page for you. Resonance, this is kind of cool. If you add a force matching the natural frequency of an oscillating object, things have this natural kind of bouncy thing that it likes to do, and if you feed into that, you can increase, what do you end up increasing? The amplitude, all right, of the vibration. Good example of this is if someone is swinging on a swing. If you push just at the right points in time, you can make them swing higher. Or how about you're a little kid and you're swinging on a swing? Don't you have to swing your legs at just the right time? If anyone's ever seen a little kid who doesn't know how to swing and they just kind of flail their legs back and forth and get nowhere, that's because they don't know how to match the natural frequency. If you match the natural frequency, you can increase your amplitude and go higher and higher. Okay? This is also the principle of being able to shatter a goblet or a wine glass. If you have a voice that matches the natural frequency of the goblet, depending on the size, it has a natural thing that it likes to vibrate at, and if you can make your voice vibrate at the same, you set up resonance and can make that shatter. There are lots of stories about marching soldiers, and that marching soldiers, when they're all marching in step, it's fine on normal ground, but when marching soldiers go across bridges, they're asked to go out of step. Because that same, if everyone pounds at the same time, they can set up a natural frequency in a bridge. The most classic and famous case of that is the Tacoma Narrows Bridge in Tacoma, Washington. There are a million different YouTubes of this and video footage of this. And that is when a newly made bridge wasn't quite constructed correctly, and the wind gusts match the natural frequency of the bridge. And if you watch that YouTube, you will see what happens to that. Some last little things here. Two-dimensional waves, like a water wave, is two-dimensional. It travels, across the plane of the surface of water. Sound electromagnetic waves are 3D. But we can draw things if it's a two-dimensional wave. Many times we draw a picture of a wavefront. I think you've seen this before. If, for instance, you have a pond and someone drops a stone in a pond, what happens? They set up ripples, right? And we often can show those ripples like this. Sometimes you might not see the whole picture, you just see a partial picture like this, and you will see these, what we call wave fronts, as they travel out. These points right here represent the crest of a wave, and this right here in the in-betweens are the troughs Okay, high amplitude, low amplitude there. And we can't see that. Notice because this is like a look down view on a wave, we can't see amplitude, but we can see what? We can see in a picture like this, this would represent the wavelength from crest to crest. And you can see the movement of the wave. All right. Last kind of cool things that happen. We don't do a lot. It just mentioned in this chapter that waves do this. There is, I mentioned this already, the law of reflection. Waves, again, can reflect when they hit a surface. And when they reflect, like a picture I showed before, the angle incident equals the angle reflective. So here would be angle incident, and this is angle reflective right there. If you have a light that comes in low, it will leave low. We do not measure from the flat plane. It's always measured from the normal. All right. There is some kind of cool videos again on a ripple tank where we can see reflection take place. Last thing that can happen again, you can have refraction. Refraction is when you have a wave and it goes from one medium into another medium where the speed is going to be different because of the change in the medium. Then interesting things happen. One is the frequency of the wave doesn't change because we said the frequency is independent of the medium. The frequency has to do whatever created the source that created the wave. So you can't change the frequency, but we know the speed changes because the medium changes. So if we can't change this, but we end up changing this, then we know this also has to change. So here is a picture, again, one of those top views of a wavefront. Wave coming in, and look at that. The wavelength shortened here, and again, changing medium, and then it also changed direction. So a wave was going like this, and it changed like this. As a wave enters a material that is denser, sometimes, and if it's light, we say optically more dense, it will bend, I think, towards the normal. So if we have here, I'm going to draw it in a normal or perpendicular. Here is the incident wave. Here is the refractive wave. So here R was reflective, here is refractive. This gets a little beyond this chapter. You just need to be aware that light can either continue straight, it can reflect, or it can refract. Okay, I think you might be armed with enough material to be able to do a worksheet. Okay, see you next time.